Good morning, friends. In the last period, we have studied about the growth and decay of the in a circuit containing L and R. In that, we have to study about how the growth can be formed in the LR circuit. Similarly, in the today's lecture, we are going to discuss about the decay. That is decay of current. Firstly, we have to study about growth. Firstly, we have to study about growth of current. Then we are going to study about what? Decay of the current. Decay of the current, in that we have to say that for the growth of the current we have to discuss. What we have to discuss, that the plug is on, what will happen, that current starts flow from its initial value, that is 0 value, to final value, and final value is near about 0.63 times I0. That is we have to discuss in the last lecture. Now the inductor is here, coil is, and the resistor is connected in series with the EMF of the battery. But now key is released. Firstly, the key is on. What will happen, that is the flow of the current in the circuit. Now the key is released, that is the inductor coil. What will happen, that its key is released, EMF is 0. When key is released, that EMF is 0. This EMF is become 0. Means what will happen, that the self-inductance is now opposed to fall of current. Self-inductance opposed to fall of current. Opposed to fall of current. Self-inductance. Then what will happen, that the EMF equation is, that is again we have to use the Kirchhoff's voltage law. That is what we have to say, that EMF is 0. And the opposition to flow of current, what we have to say, that inductor coil having the inductance is L into di by dt is equals to what we have to say, that each part of the current and resistance, that is say IR, and then finally this gets what we have to say, that minus sign here, that is L into di by dt minus IR. Separate the variables we have here, L as it is, this I and R comes in this side, and dt is here. What we have to say, that minus sign is also there, that is minus L upon IR into di, and here dt is comes. And now integrating this equation, what will happen, that when this in the equation gets integrated, what we have to say, that minus of what we have to say, that minus of L upon R into di by I, and that is equals to say of what we have to say, that dt. L upon R is the constant, so it is taken out, L by R, and integration of di upon I. This gets what we have to say, that log of to the base E, and it gets what we have to say, that di, and that is equals to integration of t plus constant of integration, say C1. This is the integration we have right here. Now finally we have to write that C is a constant of integration. Find C1. What we have to say, that T is equals to 0 and I is equals to I0. Maximum value of the current we have to here use, that is I is equals to say I0. So we have to get that minus L by R into the log to the base E of I. This is 0 plus what we have to say, that, and this is the value of say C1, and this I gets what I0, and finally substitute the value C1 is equals to minus L by R into log to the base E of I0. This is equation number, say equation 1. This gets equation say 1. This is equation say 2. Put in equation 2. What we have to get, that minus L by R into log to the base E of I is equals to what we have to say, that T as it is, and C value here minus L by R log to the base E of say I0, and now T is at one side and other terms becomes in the other side. What you have to get, that this gets the value T is equals to, this minus comes here, so plus L by R into log to the base E of I0 minus L by R log to the base E of I, log of A minus B, that is log of upon b, L by r is the constant logarithm of e to the base I0 by I. This is the value we have to consider for the equation, that is t is equals to say L by r log to the base e I0 upon I. And now we have to write, therefore here r and L goes there, this gets what we have to say, that log to the base e of I0 upon I is equals to r by L into say t, r by L into say t, taking exponential both sides. What you have to get, that logarithm goes cancel here, so I0 upon say I is equals to e raised to r by L into say t, r by L into say t. This is the value we have to consider here. Negative signs, I think there. No one. We have reversed the term. Multiplying minus sign, what we have to get, that is this gets what, I upon I0, and here sign is minus. Again here we have I upon I0, and this minus sign is there. And finally we have to write that I is equals to say I0 e raised to minus r by L into d. And this is the expression for say decay of the current. The graph of the circuit can be given in this way. This is the growth is lying like that, and decay is, you have to observe this type of the graph for the decay of the current. Here decay of the current. This is what you have to say, that I0 maximum value. This is the current flowing through the circuit. This is the initial value, and time is in this side. We have to write here, therefore this equation represents the equation of decay current in LR circuit. LR circuit. This is, after that we have to say that is obviously that the current in the circuit decay exponentially. The graph representing the decay of the current I with the time as shown in the figure. After time equals to, after time we have to say that as t is equals to say L by R, and time constant is there, so equation becomes what, I is equals to I0 e raised to minus r by L into L by R. So I is equals to I0 e raised to, this gets cancelled, that is minus 1, and this can be write that is equals to, I is equals to times I0, and what is the value of 1 upon E, and this gets what we have, 0.362 I0. This is the value of say 1 by E, and from this equation we have to write that I0 upon I is equals to say 1 by E, means we have I0 is equals to 1 by E, I is equals to 1 by E times I0. This is the final expression we have to write here. The rate of decay current in the circuit is differentiating this equation. What we have to get that di upon dt is equals to minus I0 upon say lambda e raised to minus t by lambda. This is the rate of decay we have to observe here, and that value of the decay L is equals to say decay value, that is decay constant lambda is equals to L by R. This is the value of decay of the circuit. For this we have to remember this point. From the above equation it is clear that smaller the constant lambda, more rapidly does the current die always, and decay current is the same as that of the growth current. The difference is that when the growth is, we have to observe initially key is 1, and while we study the decay, the key is release. This gets what will happen, that the inductance coil oppose the fall of current. So equation is correct, and that equation can be integrating, and finally we have to get the decay equation and time constant. That is what we have to say, that T is equals to what? L by R. This is called as time constant in LR circuit. Sometimes L and R are given. L is given in Henry, millihenry, and R is the resistance of the circuit that can be given in the value ohms and kilo ohms. We have to calculate the time constant for growth and decay for the study of LR circuit. Write down all things, these are very important. Thank you.